The topic I'd like to discuss in this video is internal convection in circular tubes. And this is the basic geometry that we are going to assume for this discussion. We are going to have a tube where the axial coordinate is given as a function of x, and we have a constant cross-section. In this case, we're going to assume that we have circular tubes. So anytime that we are referring to a P, that would be the perimeter of the tube, pi times d, and anytime that we're referring to a cross-sectional area, that'll again be pi over 4d squared. Again, pretty obvious, but this is the case where d is going to be the diameter of the tube. There are situations in the upcoming videos where we will refer to a radial coordinate, and that would be from the center line axis of the tube outward towards the wall. We have a situation that we are going to have a certain flow rate of the fluid, usually either gas or liquid, flowing through the circular tube, and a lot of times this is typically given in terms of a mass flow rate. And as we know from fluid mechanics, that mass flow rate can be given as rho times the cross-sectional area times the mean velocity. Now, the mean velocity that we will be utilizing will be dependent on whether the flow is laminar or turbulent. And we can come back to this. Again, we're going to have specific fluid properties, and these fluid properties will have to be evaluated at a specific temperature. And this specific temperature that we evaluate the properties at is going to be essentially a mean temperature of the fluid as it passes through the tube. So this is going to be another topic that we are going to have to address. Now, the flow of fluid coming into the tube can be assumed to have a uniform temperature, let's call it Ti, and we have two situations. We can either have a situation where thermal energy is added to the fluid. So in this case, Ti would be a low value, and as the fluid moves through the tube, we are constantly adding thermal energy. And in that case, the exit temperature of the fluid would be higher than the initial temperature. So this situation over here. And the inverse of that is that if we have a hot fluid flowing through the tube and we have some exterior temperature that is cooler, we would then be removing thermal energy from the tube, and in that case the initial temperature would be higher than the exit temperature. We have two base situations here that we can, and this is in terms of looking at the hydrodynamic flow. So we're not considering the thermal effects at this point. So this is a typical diagram referring to the growth of the fully developed flow. So essentially, again, you have boundary layers that grow, but in this case, of course, we're looking down a circular tube, so the boundary layer will grow inwards from a radial direction, and eventually they coalesce into a full thermally or fully developed velocity profile. Again, the region that's not contained within the forming boundary layers is considered the irrotational core. And if this is the velocity boundary layer, we then produce at some point known as the entry length, we will then end up with a fully developed profile. And what this means by a fully developed profile is that this velocity profile, where you have a high velocity at the core and that uniformly decreasing to a zero velocity at the no slip condition at the wall, will be maintained throughout the rest of the fluid as it passes through the pipe. So you have two regions. You have what's referred to as the entrance the entrance length, and then the rest of the tube, as long as it's a straight tube, would be considered a fully developed region. Now, for laminar flow, you get this nice parabolic profile, and if we were interested in the average velocity, and you can show this analytically, as you did last semester, the average velocity will be half of the maximum velocity. Just quickly be aware that I'm pulling some of these diagrams from different books, so sometimes we will say V for the velocity, and sometimes it'll be U for the velocity, but that should be pretty simple for you to pull out of context. And lastly, we have for turbulent flow, we have a much flatter profile, and it's only in this, what is referred to as this viscous sublayer, is where you have the quick drop off of velocity. So in this situation, it's usually appropriate to assume that the average velocity and the maximum velocity are essentially the same. Okay, so now let's get into the discussion of the thermal characteristics. What I have down here, calling the thermal flow profile, this is out of a textbook, and what they're showing here is that if you have a wall temperature, say it's constant in this case, and the fluid comes in at a temperature that's less than the wall temperature, well, you're going to end up with a profile that looks something like this, where the fluid at the interior of the pipe near the center line is going to be at a temperature lower than the surface temperature. And then as you move further out towards the wall, the liquid is going to get warmer and eventually be at the same temperature as the surface temperature for the fluid that is right next to the wall. And you can take this and create an average, and we would refer to that as the mean temperature. So we have three temperature quantities up here. So we have the mean temperature of the fluid, and that, if we're going to continually put energy into the fluid as the fluid moves in the x direction, this mean temperature will be a function of x. Now the surface temperature, depending on the way we're moving energy into or out of the tube, this surface temperature may or may not be a function of x. In other words, if we say we have a constant temperature wall, well, then the surface temperature wouldn't be a function of x. But if we have a situation where, say, we have a constant flux of energy into the wall, into the tube, well, then the surface temperature might be increasing as you move along the tube. So the surface temperature in that case could be a function of x. And the last one is our local temperature. So what is the temperature exactly at this location? Well, it's going to be some x distance from wherever we started measuring x and at some r location. So in this case, the local temperature is a function of two coordinates, the cylindrical coordinates that we would use to define a location within the tube. Now, what I'm showing over here on the right is something that's going to show up in the next couple slides. And what I've chosen to do is, let's make a simplified velocity profile. This is not an actual velocity profile. All the velocity profiles will have some curved profile here. But what I'm choosing to do is make it a triangular, so a very, just linear velocity gradients, so that I can show how the velocity profiles can change under our different conditions. And those different conditions are going to be defined by this definition of a thermally fully developed flow. So we have a fairly, I'm not going to say it's complex, but it's an interesting equation. And what we're doing here is that this quantity inside the brackets here that you're taking the derivative of, this is referred to as the non-dimensional temperature. So if we do that, if we say that this is the fluid, the temperature that we are going to use to define the flow. So surface temperature minus the local temperature, right? Well, let me back away from this. Say it another way. This is the temperature profile, right? So at any given location within the fluid, we should be able to find out what the temperature is, and if we have a common temperature along the wall, or we have a profile that's not changing, this would be given by the temperature, the local temperature. So instead of using just that, we're choosing to use a non-dimensional form. So we have the surface temperature minus the local temperature divided by the surface temperature minus the mean temperature. And you might say, well, where does that come from? Well, that's coming from a more sophisticated analysis, but what we basically say is that if that non-dimensional temperature remains constant as the fluid moves from entrance, or from once the flow gets fully developed, as it moves along the pipe, if this does not change, the quantity does not change, or if this is a constant, then the derivative of that with respect to x will be equal to 0. So what this expression implies is that while the temperature profile, right, this term will continue to change with x, the relative shape of the profile no longer changes, and the flow is said to be thermally fully developed. Now, this relative shape term, well, we're in the next couple of slides, we're going to try to explain what that says, but nonetheless, it refers to a methodology or a way of deciding when a flow can be said to be fully developed in the thermal sense. So now, the condition of thermally fully developed flow is reached for two different types of situations. Either a uniform surface heat flux, so the heat flux into the pipe is constant, or we have a uniform surface temperature. But in those two cases, there's two different things that are happening. So this one, if you have a constant heat flux into the pipe, then the surface temperature is going to end up varying as a function of x. And the opposite is true, that if you have a constant surface temperature, well, then your heat flux is going to vary as a function of x. So the condition of thermally fully developed flow is reached or takes place for two different situations. And the first one is having a uniform heat flux into a tube, or a tube that has a constant surface temperature. Both of these imply something. So if you have a constant heat flux into the pipe or tube, that is going to imply that your surface temperature has to vary. And conversely, if you're saying that you have a constant surface temperature, then in order to maintain a constant surface temperature, the heat flux into the pipe is going to vary as a function of x. So you have two things going on here. Okay, now before we actually look at the profiles, we can look at the implications of having a fully thermally developed flow. So if we take that condition that we've defined as being a fully developed thermal situation within our flow, and we combine that with our definition of heat transfer, convective heat transfer given by Newton's law of cooling, or heating in this case, again, this analysis is taken care of in the textbook, and in a more formal sense. But if you take these two conditions and combine them, what you're going to end up with is a situation that implies that the heat transfer coefficient, the local heat transfer coefficient, does not change as a function of x. So what we're basically saying here is h as a function of x is a constant. And that's shown over here in this plot. And it's very, very similar to, well, it's an exact corollary, really, of the fact that the friction factor changes. It has a very, very high friction factor. If you remember right, the fluid has to go from a given velocity to zero velocity right at the leading edge when it meets the surface. So you have a very, very high shear stress, which is directly proportional to the friction factor. But then after the fluid becomes fully developed, see, we have two different boundary layers here. This is the fluid boundary layer, the hydrodynamic or velocity boundary layer, and our friction factor remains constant. And that's shown over here in case you don't remember. There is always this fully developed or dotted line that shows when the fluid is fully turbulent, and after that the friction factor becomes a constant. Well, we have the exact same situation for the thermal boundary layer. So once we have a fully developed flow in the thermal sense, once the thermal boundary layers coalesce, we again reach a situation where the local heat transfer coefficient is constant. Now, we will have to take a look at specific problems, because there are some problems where the fluid running through the pipe might be developing through the whole course of the length of pipe that we're interested in, and we would have a varying local heat transfer coefficient. But for long pipes in different situations, this situation is true, and that comes as a direct result of applying these two conditions. So we will be taking a look at this as we move forward. All right, so now let's take a quick look at different situations. So what we have over here is the situation where we have a constant heat flux into the tube. So what's happening here? So all of these arrows here are saying that you have a constant heat flux, so many watts per square meter coming into the fluid. So if we have a profile that starts like this at station X1, so this small line here is the temperature of the fluid at the center line, and the line out here at the wall is showing us what the temperature of the surface temperature is at that X location. And then as we move down from station 1 to station 2 to station 3 to station 4, what we see is that the profile, the leading edge profile, or the profile of the fluid, doesn't change. But what is happening is that there's a uniform growth of temperature. And you can essentially see that here, right? You know, that there's basically an added box of warmer fluid that keeps moving in, and the surface temperature keeps growing. So that's shown here from an analytical standpoint. If we look at Newton's law of cooling here, where we know that H is going to be a constant, and in this case, the surface flux is also going to be a constant, well, we can rearrange the equation and we get this situation where Q over H equals Ts minus Tm, but that has to be a constant. Now, if I take the derivative of this constant term, we get that the derivative of a constant is equal to 0, and as a consequence, we have a situation where the rate of change in the x direction of Ts, the surface temperature, equals the rate of change of the mean fluid temperature. And this is shown very clearly in a plot over here. So you have this entrance region where you don't exactly know what's happening. Well, we do, but the change of the surface temperature is not linear. And then as you get into the fully developed region, the slope of the surface temperature exactly equals the slope of the mean temperature. And what they're showing here in this situation is from another textbook, but they're basically showing that the assumption is that the inlet and outlet temperatures of fluid in a pipe will also have a linear profile for situations where you have the input energy, the heat flux, is a constant term. Now, the other thing that's implied here is that, again, I'm showing here that if you have, say that this is the change, oops, wrong way. Consider that this is always the delta T. So this is delta T for this delta X. So what I'm showing here is dt dx. And this basic growth is happening every time I move from station 1 to station 2. I have a dt dx. From station 2 to station 3, I have a dt dx. And that's remaining a constant value. And what you're seeing here is that if you take this situation where the change in TS, the surface temperature, is equal to the rate of change of the mean temperature, and you take that situation and you plug that into this requirement of the thermally fully developed flow, the result is that not only do you get that these two have equal temperature gradients, but all three of them do. So the local temperature changes as a function of the surface temperature, which again changes as a function of the mean temperature. Now, one of the things that's not as obvious is that if the temperature of the surface only changes as a function of x, notice it's a full derivative, and the mean temperature only changes as a function of x, well, then that implies that even though this is a partial derivative, right? This is dx of t, which is a function of r and x, but this equation implies that this derivative is solely a function of x. So what that means is that at every r location, right, the change as we move down is constant, and then as we move out, it's a different value, but it's a constant value. So that if we started out with this distance and then we have this distance, it's a set change that's being applied all the way through the fluid. So that means that this profile doesn't change. So for thermally developed, fully developed flow, where the situation is that we have a constant heat flux, the actual shape of the profile does not change. Now we have the situation where we have a constant surface temperature. Well, this is shown here. So let's say that this is a line that defines the magnitude of the surface temperature. So the fluid comes in cold, and what happens is you have this really sharp gradient because we have cold fluid, and then the fluid has to have the surface temperature when it reaches the wall. And then what you're essentially getting is that as you move down, or as you move from x1 to x2, and thermal energy is coming into the fluid, well, that thermal energy works its way further in, causing the core to get warmer and warmer. And eventually, you'd of course reach a situation where the entire fluid throughout the pipe is going to equal the surface temperature. And it can't get any warmer than that, right? So this is a limiting factor. And what you're going to show over here is that, again, the mathematics will and the analysis show it, but what we have here is it's not a linear change in temperature between the entrance and the exit. There is this logarithmic change in the profile. And we're going to refer to that as the log mean temperature when we get into that in the next video. So if we define, again, this is our fully thermally developed profile, and in this case, we end up with, if I take the derivative of this and substitute in where Ts is a constant, you get this, and again, initially hard to interpret equation. But what's this really showing is that we're looking at what happens to the local temperature as it progresses down in the x coordinate. Well, Ts is a constant. Now, the mean temperature is only varying as a function of x, so this derivative only varies as a function of x, but we have this last term, right, the local temperature. So this local temperature is going to vary as a function of r. So that means that the temperature gradient is also a function of r. So the shape of the fully developed thermal profile will change as a function of x. Sorry, I read that wrong. The axial temperature gradient is a function of r. So the shape of the thermal profile changes as x moves down. And you can also see that in the situation that this expression, the local temperature, is going to be less here, right? It's going to be its lowest value. At any given x location, the temperature at r equaling 0 is going to be the lowest, the smallest term. And then as you move out, the temperature, as I increase r, will get warmer. So if this is at r equaling 0, dt dx is going to be a maximum value, right? Because this is a subtractive term, right? So if I have Ts minus, and this is a small value, well then dt dx is going to have its maximum value. So I have a high gradient here. So you can see this rapid change at the core, but then the gradient here changes at a slower value. And that allows the core to essentially catch up with the wall temperature. And stating that, we get dt dx decreases as r increases because this term has a minimum value when r equals 0. All right, so that gives us the basic understanding of what's happening to fluid flowing within the tube under the two different conditions that we will refer to as fully thermally developed flow. And then the next step that we really have is to determine what is the H value, right? If we have Q double prime equals H delta T, well, we still need to know what H is to fully define what's going on within our flow field. So that's going to lead us into the next set of the next video, where we'll discuss the energy balance. That'll then give us an ability to create correlations for the Nusselt number that will then reveal our value of the heat transfer coefficient.